Hi, my name is Emma, and I'll be talking about creating a blood flow model in COMSOL. So why is creating blood flow models important? According to the CDC, heart disease is the leading cause of death in the United States. The primary cause is atherosclerosis, which is the buildup of fatty substances along the vessel wall. This creates a narrowing in the vessel, which in turn changes the blood flow behavior. Aneurysms are another source of heart disease in which the weakening of the vessel wall results in a ballooning of the vessel. This also creates abnormal flow behavior where recirculation in these dilations begins to happen. The goal of this study is to investigate how these changes in geometry can affect the flow behavior. So in this study, we'll look at 3 different cases. One will be a normal blood vessel, which is just modeled by a straight cylindrical tube. 2 will be stenosis, which is just the narrowing of the blood vessel, and so we'll use an indentation to simulate fatty buildup. And then 3 is the aneurysm, in which we'll use a circular ballooning to simulate wall weakening. So for all of these cases, we'll look at both steady flow and then a transient study. And so in both models, the no-slip condition at the walls and the pressure condition to simulate a traction-free state at the outlet will remain constant. The only thing that will change is the velocity condition at the inlet. So in the steady state flow, we'll have a constant inlet velocity, whereas for the transient flow, we'll have a sinusoidal function at the inlet, which will simulate a pulsating flow to mimic true blood flow behavior. So now we'll get into the steady state results. So first, looking at the velocity fields, we can see in the normal condition that the velocity profile develops into becoming fully developed and then kind of remains constant throughout the blood vessel, whereas in the stenosis, we see that as it hits that narrowing, there is a steep increase in the velocity magnitude. And then with the aneurysm, we can see that some of that flow is being directed into the aneurysm itself, causing a circulation. Streamlines are also important to visualize the circulation that's happening in both of these models. With the stenosis, we can see that there is a small circulation occurring right behind the narrowing. And then with the aneurysm, we can obviously see that there is a circulation happening within the aneurysm itself. And so it's important to make note of these circulations because they can contribute to the unsteadiness of the velocity and increase turbulence in the flow. Wall shear stress is also an important factor to consider because this can affect how the biological tissue behaves when these conditions change. So in a normal condition, the wall shear stress remains relatively low and relatively constant, whereas in stenosis, there is an increase in the values of wall shear stress right around the narrowing. And then for an aneurysm, we see a small increase in the wall shear stress right at the edge of the aneurysm. The results from the stenosis model are validated against data and literature where we're seeing a high agreement in the velocity and wall shear stress fields between their results and my results. So now we'll move to the transient results. So this is the pulsating flow. So here shows the pulsating behavior of the blood vessel, showing an increased magnitude of velocity at the height of each pulse. Here we can see the pulsating behavior of the stenosis model, where we can see there's an increase in velocity at that narrowing, which is amplified with each pulse. And then here's the pulsating behavior of the aneurysm, where each pulse allows us to really see that circulation and flow that's occurring within the aneurysm itself. So from these studies, we can conclude that the stenosis model, there is an increase in velocity in the stenosis, in turn causing recirculation and increased wall shear stress. In the aneurysm model, there is a flow velocity with circulation within the aneurysm itself, and there is an increase in wall shear stress at the edges of the aneurysm. It's important to look at these changes in blood flow behavior because different conditions can affect the cellular and inflammatory response of the vessel walls that contribute to cardiovascular diseases. These models can also be helpful in evaluating treatment interventions because it can give insight into the best treatment plan based on the flow behavior response. These models can also be implemented with other models like constitutive models of vessel wall mechanics to create a more comprehensive and accurate model. Thank you.